All right. Hello, everybody. Let's get started. One second. All right. So today we're going to talk a bit more about circuit design. We have seen binary addition and subtraction in week 1. We talked about Boolean algebra in week 2. And today we're going to see how they come together, and you can use the knowledge you learned from Boolean algebra to build the hardware circuitry to realize those addition and subtraction in binary. And then we're going to move on to the next powerful tool, that is Karnaugh map. This is a tool that can help us simplify our task of logic simplification. Boolean algebra is nice, but it's kind of hard to deal with. I know that people are suffering through like Monday's workbook for those Boolean simplification questions. You really have to spend a lot of time just trying out different things to find out the best optimization sequence. And today we're going to see a better tool, a visual way to do logic minimization. That is, even though it's not as scalable as Boolean algebra, this works pretty well for like small functions with 4 variables, 3 variables, and things of that sort. All right. So the first topic is about designing a binary adder. The first circuit that we saw in this lecture is actually an adder circuit. This is before we even discussed the axioms and theorems of Boolean algebra. I showed you just one example where you can convert some behavior specification of 1-bit binary addition into a truth table. You can derive the expression from that truth table by just mapping the two output functions into corresponding gates. So sum is an XOR gate. Sum is 1 when inputs are different. Carry is 1 when both of the inputs are 1s. So one of them is an XOR gate. The other of them is an AND gate. We can put the XOR gate, AND gate, connect them to the same inputs, send them to different outputs to realize this circuit. Right? This is the implementation process, the conversion from a high-level description to a very low-level implementation. All right? But in reality, we don't just need a 1-bit adder. We also need 4-bit adders. Right? When we do binary addition, it's always multi-bit addition. So a 4-bit adder should work as follows. It should take in 2 4-bit inputs, input A with 4 bits, input B with 4 bits, and produce a 4-bit sum, and also a carryout. Right? And that is sort of illustrated by this diagram over here. This is what we're trying to build. The circuit also has a carry in. Right? Even though typically when you do 4-bit addition, you don't need a carry in at the very beginning. Right? But think about concatenating this adder with another 4-bit adder. Having that additional carry in allows you to put multiple copies of this 4-bit adder back to back to create a wider adder. Right? So it's like a part of a modular design. Right? Having that carry in allows you to put together multiple 4-bit adders to build an 8-bit adder, 16-bit adder, and even 32, 64-bit adder, etc. And hopefully, I can send in my 2 4-bit inputs, let's say 0011 and 0101, at the A inputs and B inputs, and get my sum at the bottom. All right. So to build a 4-bit header, we need a slightly more capable 1-bit header. The 1-bit header we saw earlier does not have a carry in. So you cannot connect in this copy of the 1-bit header to the next copy because the carry cannot be used as an input for the next bit. And therefore, to solve that problem, what we're building here is a full adder. So a full adder is just a half adder, the one that we saw earlier, plus an additional carry in. And this carry in and carry out allows you to put multiple copies of this adder, use the carry out of the first bit as the carry out of the second bit, use the carry out of the second bit as the carry in of the third bit. Right. So this full adder works as follows. You have 3-bit inputs. X, Y are your data, the 2 input operands. And then C is the carry from the previous bit. And then based on these 3 inputs, I'm going to do an accumulation of these 3 bits to produce a sum and produce a carry. Right? And we can look at its behavior from the truth table. If all of the inputs are zeros, you're just taking the accumulation of these 3 numbers, you get 0, 0. If one of them is a 1, let's say in this situation, and this situation, right? One of the 3 input bits is a 1. You have a sum of 1, carry of 0. The result is 0 plus 0 plus 1 is a 1, which can be represented as a 1 at the output without a carryout. If you have 2 of the inputs being 1s, let's say this case, and this case, again, we're doing an accumulation of those 3 bits. 1 plus 0 plus 1 gives you a sum of 0, a carry of 1. Right? The magnitude is 2, and 2 has to be represented as a carry at the next bit. So you have a carry of 1, sum of 0. And finally, if all of them are 1s, which essentially corresponds to a scenario where your current bit is 1, 1, but you also have a carry from the previous bit. Right? So if I do addition of 0, 0, 1, 1 plus 0, 0, 1, 1, if I look at the second bit position, it receives a carry in of 1 from the previous bit. So in the second bit, right, the second column from the right, I need to do an addition of 3 1s. So 3 1s gives you a magnitude of 3, and that needs to be represented by a sum of 1 and a carry of 1. Right? So carry has twice the positional weights, so send the carry to the next bit, and then you still have a 1 at the end of the sum bit. Yeah, any questions? All right, just to recap for those of you coming late, we're trying to design a 4-bit adder, a 4-bit binary adder. And to do that, we need to use 4 1-bit adder that can be connected back-to-back. To allow this back-to-back connection, we add 1 additional input port to our original 1-bit adder, the carry in, so that you can use this maybe your first bit for binary addition, and then the carry out can be sent to the carry in of the next bit, right, to form a chain of adders to realize multi-bit addition. And here's the truth table for that full adder. And this truth table can be implemented as a Boolean circuit. If you look at the sum is 1 when your inputs is 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, whenever you have an odd number of 1s at the inputs. So that is an XOR function. Right. The carry logic is a little bit more complicated. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. It's kind of hard to describe that using a single gate. But think about it. For a 1-bit binary addition with a carry in, you would have a carry out if 2 out of the 3 inputs are 1s, right? More than 2 out of the 3 inputs are 1s. So 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1, those are the 4 cases. And you can represent it as a sum of products, a summation of 3 different conditions. When x and y are both 1s, you want the output of carry out to be a 1. If x and carry in are 1s, again, you want the carry out to be a 1. Y and carry in are 1s, you want the output to be the output of carry out to be a 1. Right? If all of them are 1s, x and y and c in, again, they'll make the carry out a 1. So sum of products, you can describe it as a summation of 3 different conditions and implement each of those conditions as an AND gate. Right? These 2 are 1s, these 2 are 1s, these 2 are 1s, OR them together. That are all the conditions that you should have a carry out of 1. So that is a 1-bit full adder. Now, I'm just representing that 1-bit full adder as this block symbol with 3 inputs. You have 2 from your input data. One of them is a carry in from the previous bit, and then produce a sum and carry. Right? There's an arrow representing the direction of data flow. So each full adder sends the carry out to the carry in of the next full adder, right? And that forms a carry chain. And this carry chain allows us to connect multiple bits together to create a wider adder. Again, now if I have some input data, I will break it down into 4 individual bits. The B value, that is a 4-bit value, I will break it down into 4 individual bits and then send them into the corresponding full adders. And then carry in, for now, is just a 0. When doing a 4-bit addition, the first position does not have a carry in. So you can just think of this as a 0 for now. All right. So let's try to plug in some of the binary numbers and see if it works. Anyone want to give me a 4-bit binary number? 1, 1, 0, 0. I'll use that as my number A. Right? Break it down into 4 bits based on its positional weights. Send it to the 4 separate full adders. Give me a second number. Someone. 4 ones. I'll use a different color. Eric, you're really going after those more complicated cases. All right, so let's do addition. And then this is a combinational circuit. So evaluation happens from the inputs to the outputs. Right? And this full adder already have the 3 inputs fully specified. So I'm going to do evaluation from this bit and moving on to the more left bits. So 0, 1, 0 from the truth table for full adder, that's a single one. So sum is 1. Carry is a 0. Right? Based on, so this full adder will just evaluate by itself based on its truth table. The second bit, 0, 1, 0. Sum is 1. Carry is 0. Right, third bit, 1, 1, 0. So sum is 0. Carry is 1. And next bit, 1, 1, 1. Sum is 1. Carry out is a 1. So if I were to write those numbers in decimal, 1, 1, 0, 0. 1, 1, 0, 0 is my number 12. 1, 1, 1, 1 is my number 15. I would get an overflow, right? Because the result is greater than 15. So this should be an overflow condition for unsigned addition. And indeed, I do have a carryout. And for unsigned addition, carryout indicates overflow. Right? But if I were to look at the magnitude, well, what do I actually get if, let's say, I have one additional bit to accommodate that carryout? Right? Then this would be 16, positional weight of 16, positional weight of 8, positional weight of 2, positional weight of 1, which indeed gives me 27. So it would be a correct result if I have 5 bits to accommodate the sum. Right? But within 4 bits, I do get an overflow, right, by having a carryout for this unsigned addition. So everything works just fine. Right? Essentially, this is no different from the column method. You line up the two numbers, A and B, and then you represent the carry as a dot on top of the next position. That's essentially how this circuit is implemented. Yeah. Any questions? All right. If there's no question, I have an exercise for you. I want you to build a full subtractor. Right, so 1-bit full adder, taking 3 inputs, x and y, and carry in, produce 2 outputs, sum and carry out. A 1-bit subtractor works in a similar way, takes 3 inputs, x and y, those are from your input data, and the borrow in, which is the borrow needed by the previous bit. And then might need to borrow from the next bit, which will be represented as a borrow out of 1. So maybe let me write down an example. Let's say 0, 0, 1, 0 minus 0, 1, 0, 0. Right. Well, this is a bit problematic. I'm going to use a simpler one. Let's say 0, 1, 0, 0, 0, 0, 1, 1. Right, to make sure that the result is still an unsigned number. So what's going to happen is that at every bit position, I'm going to evaluate 0 minus 1. But also considering if there's a borrow needed by the previous bit. So 0 minus 1 should give you a difference of 1 and a borrow out of 1. 0 is smaller than 1, so it needs to borrow from the next bit, which is represented as a borrow out of 1. So what I just did is really the column 1, b equals 0, x equals 0, y equals 1. In that situation, borrow out will be 1. I need to borrow from the next bit. And difference is 1. So after borrowing, I essentially have a positional weight of 2 in the current column. So 2 minus 1 gives you 1. Right. Yeah, could you spend a few minutes, try to fill out this table as much as possible, and then we'll see how we can implement that as a Boolean circuit. I'll give you one more minute. You don't have to complete it. Just fill out a few rows, and then I'll get you into a group discussion with some of your classmates, and then you can explain to each other how you think about this problem. Right. So what I'm really doing is I'm subtracting y and borrow in from x. X minus y minus borrow in. All right, time is up. Can we get into groups of 2-3 people and then discuss a little bit how you think about this problem? Like for the rows that you already filled out, and if you run into any troubles, maybe your classmates can help you answer some of your concerns. Right. So yeah, Eric, if you can, could you get together with Michael and Rona, Hamza? You may want to get together towards the middle and then form into groups of 2-3 people, up to you. Did you run into any troubles, like any specific case that you find particularly difficult? Or no? So for that last row, 1, 1, 1, right? 1 minus 1 minus 1, right? That's essentially where we're trying to compute. Sum would be a 1. Borrow would be a 1, right? So how do you think about it? Like, people think of these binary numbers in different ways. I think of it as just 1 minus 1 minus 1, and then I plus 2 by borrowing from the next position, and then do the binary subtraction. What about you? Like,
I borrowed, so I just added 2 immediately.
I see. So you directly add 2 to one of your inputs, like input x. So think of it as a 3. What about you, Judy?
I think I think of it in a
I see. So x is like the positive number, y and b in, those are negative numbers. So I see. Sounds good. Did you guys run into any problems?
So I have a question.
Yeah.
So we know adder you can use we're trying to do a circuit representation of the adder.
Mm-hmm.
So we know adder you can essentially make OR and AND gates that you'll do something with it. I'm pretty sure adder will fix it. For subtraction, one of my biggest concerns is that the row 0, 1, 1, right? 0 minus 1 minus 1. What's the difference? 1? It should be 2, right?
0 minus 1 minus 1.
Yeah. What's the difference?
BL would be, you need to borrow, right? 0 is smaller than negative 2.
Yeah.
So you need to borrow. And the difference will be 0.
Oh, so
because I borrow 2 from the next column. So really I'm doing 2 minus 1 minus 1, which gives you a 0.
you can use XOR?
Yeah, you can also use XOR gate for the difference, I suppose. Yeah, but I have to see the full table to really, try to verify that pattern.
Oh, I see.
Yeah. So the implementation depends on all the rows of the truth table. So we really have to fill it out entirely to see, if we can build it with a single gate or, with multiple gates, which gates and how they are composed.
So difference, or just because, I just started noticing that when there's like odd number,
Yeah.
like ones,
Yeah.
it's a 1. When it's even number,
That's right. Yeah, that's a nice observation.
so actually has to work with it, but I don't know about the B out.
The B out. Yeah, we'll see. We'll see. All right, guys, time's up. Oh, yeah. So what's going on in this group? What did you find?
We're still filling it out.
Yeah, so how many rows have you filled out? 5. I see. That's not bad. Yeah, you don't have to really complete it. So just know the idea, and then, with enough time, eventually, I'm sure you can get it done. Right. So subtraction is a little bit harder to reason compared to addition. Right? For addition, you're just adding together 3 numbers, and they have the same kind of positive positional weights of 1. So immediately 0, 0, 1, 1, 0, 0, 0, 1, 0, you know that it will have the same result. Right? So you can figure it out group by group rather than for individual rows. Subtractor, sometimes you can still sort of think about it as, y and b in have the same negative positional weights. Right? Both of them represent essentially -1. So these 2 rows would have, for example, the same output. And that can make your job a little bit easier by doing some grouping first and then approach it by reasoning about binary numbers. Right? So let's do them together, one by one. So 0 minus 0 minus 0, just all 0. Right? 0, 0 minus 1. And 0 is smaller than 1, so you need to borrow from the next column. So that becomes a 2. 2 minus 1 gives you a 1. So borrow and difference are both 1s. Right? Again, I said these 2 columns should be the same. X minus y minus b in is the same as x minus b in minus y. Okay? So this is also 1, 1. You don't have to, exactly reason about what is happening for that particular case, right? By observing that there are some rows that should behave identically. 0 minus 1 minus 1. I definitely need to borrow. Right? Once I borrow 2 from the next column, right? 2 minus 1 gives you a 0. Right? And then 1 minus 0 minus 0. 1 is greater than 0, so difference is 1. I don't need to borrow. 1 minus 0 minus 1 is just 1 minus 1, which is 0. So 0, 0 on both. 1 minus 1 is 0, 0. Again, these 2 columns should be the same. And then finally, 1 minus 1 minus 1. It's actually no different from 0 minus 1. So it is 1, 1. All right. Does it make sense? Cool. Now if we were to compare the adder and subtractor, right, see this sum column, it's actually the same as the difference column over there. These 2 columns are exactly the same. And Max told me earlier that this is one thing that he observed. So Max, how did you observe it? Do you have like a more binary reasoning, or is it more like by looking at the truth table?
No, there's a binary reasoning, right?
Yeah.
Like if you really think about it, if there's like an odd number of 1s, the difference has to be 1, right? Like if you really think about it, because there's no other way for it to become 0, because there's only 1 or 0, right? So if there's even number of 1s, it has to be 0, because it has to subtract out somehow, right?
Yeah. If it's odd number of 1s, that's true, right? 1 minus 0, or like 0 minus 1 minus 0, you're off with 0 by an odd number of 1s, right? Even though it's on the negative side and sometimes on the positive side, like 1 minus 0, you're always off with 0 by an odd number of 1s. So that's the reason why difference can again be implemented as an XOR gate. Adder is kind of easier to reason. That is, when 3 of them are 1, so you get either 1 or 3 at the output, right? And that is an XOR function, an odd number of 1s producing a 1. Over there, you sort of, when you have an odd number of 1s, you get either positive 1 or a negative 1. Negative 1, when you have a borrow, again becomes a positive 1. So you have a difference of 1 when an odd number of inputs are 1s. Right? That's the binary reasoning as for why we use an XOR gate to implement the diff. Borrow out. Borrow out is kind of different from the carry out. Right? They're not that different, actually. So if you look at these 4 positions and these 4 positions, right, they're the same. If you look at this group of 4 and this group of 4, they're the same. I'm just shuffling the top half and the bottom half of the truth table. Right? But that requires an entirely new implementation. You can represent it as a 2-level SOP, of course, because any function can be written as a 2-level SOP. How do we write it? We'll see that in 1 second. Right? You can approach it from a Boolean algebra perspective by collecting all the minterms, right? Represent it as a sum of minterm expression, and then perform some manipulation. Or I can more conceptually think of it as having, I would say, like 2 zeros, 2 zeros. Well, not exactly. So 3 ones, 2 1. I'm trying to find the 0 and 1 pattern in that borrow out column to see if there's an intuitive way to implement it. Right, for the adder, what we can do is when we have 2 or more 1s at the inputs, so carry out is a 1. For borrow, I haven't seen that intuitive reasoning yet. 3 1s. No, yeah, I probably have to go through Boolean algebra to find the SOP. Right? It's always doable, but not as intuitive as an adder. Right? But remember, today we're going to talk about Karnaugh map, which is a very nice tool for implementing any 3-variable, 4-variable Boolean expression. And once we get there, implementation of this will be trivial. Yeah. Any questions? All right. So let's come back to this 4-bit adder. Do you think I can use it to implement 2's complement addition? I have been dealing with unsigned numbers, which works perfectly fine. What about 2's complement? I think about the difference between these 2 addition algorithms, right, in terms of the bit-by-bit calculation rules and how we handle when we reach the end. Do you think it will work? Any ideas? Yes, Eric. Yeah, it will work if you just remove the last C4. So binary addition is essentially the same as unsigned addition, except that you throw away the carryout. So let's say I can use the very same number that we used earlier, which is 1 1 0 0 plus 1 1 1 1. 1 1 0 0 is a -4. 1 1 1 1 is a -1. Right, so I should get a -5. Again, I run through the binary addition. The carry in will be 0 because I'm now using it. 0 gives you 1 0 1 0 0 1 1 and 1. If I just ignore the carry out, and then what I get at these 4 bits would mean that's indeed a -5. You flip it, add 1, that is the magnitude. So 0 1 0 0 plus 1 0 1 0 1, that's +5. So this number is -5. Right? That's work. That's work for binary addition as well. For unsigned addition, carry out indicates overflow. For 2's complement addition, carry out does not equal overflow. So I do not yet have the overflow detection logic with this 4-bit adder implementation. But in terms of the sum, if there's no overflow, this will always be the correct sum. Right? Just because binary 2's complement addition works in a very similar fashion to unsigned addition. And in the workbook, you'll try to implement the overflow detection logic based on top of this 4-bit adder. Right? Based on this structure, sum is correct. And you need to add a bit additional processing logic to calculate the final carryout. Sorry, the overflow logic for 2's complement. All right. So if you need a 4-bit subtractor, one way of doing it is to implement 1-bit subtractor, as you did in our practice earlier. Right? That's 1-bit full subtractor. You put 4 of them together, you get a 4-bit subtractor. The other way to do subtraction is by reusing your 4-bit adder. And this is based on essentially the observation of 2's complement. subtraction, A minus B, is no different from complementing B and then do an addition. And how do I complement B into its complement? I flip each individual bit and then add 1 to it. That's where that I use carry in comes to be very helpful. We can set it to a constant 1 and then flip each individual bit from the B inputs. And then essentially this will give you the subtraction between those two numbers. Right. Again, I just want to use the same example as before. 1, 1, 0, 0. Well, actually, I need some example for unsigned addition. Right. So maybe I'll do 1, 1, 0, 0 minus 0, 0, 1, 1. So 1, 1, 0, 0 in unsigned represents 12. 0, 0, 1, 1 in unsigned represents 3. So I should get a 9 at the output. So if I follow this circuitry, I probably first want to complement B, right, to get those intermediate results. So 0, 0, 1, 1 becomes 1, 1, 0, 0 after inversion. The carry in is a 1. And then again, starting from the least significant bit, I'm going to do actually addition and hoping that the result is a valid subtraction result. 0, 0, 1 gives you a 1, carry out of 0. 0, 0, 0 gives you a 0, carry out of 0. 1, 1, 0 gives you a 0 with a carry out of 1. 1, 1, 1 gives you a 1 with a carry out of 1. We're sort of using those numbers in terms of their two's complement representation. And what do I get as the result in terms of an unsigned number? Right, this is an unsigned number 9, which is correct. Right, we're applying the two's complement principle to convert a subtraction into an addition by flipping the second input variable and then add 1 to it. Right, in fact, you can also flip. Well, you cannot flip A. You have to flip B, right, to get the essentially negative B, and then do an addition. This is actually the beauty of the kind of connection between binary and Boolean algebra. In binary, we can develop this addition and subtraction algorithms. And as it turns out, you only need to build one copy of a 4-bit adder to do many things, to do unsigned addition, to do two's complement addition, to also do unsigned subtraction. Right? So in your hardware, you just have to build a circuit once with a bit of additional switching or processing logic before your inputs to repurpose the same hardware for different computations. So let's say you have an area that can fit 8 adders or 8 subtractors. Right now, you can probably put down 7 of these reconfigurable adder subtractor and be able to realize a much wider range of computations. Right? It gives you better flexibility by being able to adapting your hardware for different purposes. All right. So with that, I'm going to show you how this thing actually works by giving you a demonstration. And you can open that link. OK, 1 second. I created a shared project that has some of these components. And then you can check out that link later. So this is a 4-bit adder subtractor with 4 full adders. So each of these blocks is a 1-bit full adder, and some additional XOR gates at the inputs that connects between B and some operation selection variable. Right. So if operation is 0, all of the XOR gates will be transparent. 0 XOR anything is that original variable. Right. So each adder will receive A input and B input, A input or B input. So A1, B1, A0, B0. When the operation is a 0 and 0 going through the XOR gate does not affect your input variable. So when OP is 0, this works as an adder. So let's say if I have this number 0001 plus 0001, I get 0010. 1 plus 1 equals 2. Right? So 1 plus 3 equals 4. 3 plus 3 equals 6. Right? I can do many of these additions. So when OP is 0, the whole circuit works as an adder. When OP equals 1, it does two things to my adder circuit. Number one, it's sending in that carrying of 1 to the first adder bit. Secondly, 1 controlling the XOR gate in your workbook that works as an inverter. Right, so now you're inverting your B inputs, flipping each individual bit of the B inputs, and then adding an extra 1 from the initial carry in. So now this should work as a subtractor. Again, right now my input is 0, 0, 1, 1, minus 0, 0, 1, 1, I get a 0. Right? If it's 3 minus 2, I get a 1. So 0, 1, 1, 1, that is my A is 7. 0, 0, 1, 0, B is 2. So 7 minus 2 gives you 5. And you can just play with the circuits and then do a bunch of subtractions. Yes? That is the overflow detection for 2's complement. Right? So for now, you can ignore it. That is something that you will implement in your workbook. But the reason why we have an XOR gate is roughly as follows. The most significant bit of 2's complement determines the overflow condition. If you add together two positive numbers, you get a negative number. So 0 plus 0 gives you a 1. That's an overflow condition. You can describe the overflow condition in terms of the 2 input bits and the single output bit. Right? 3-bit going through some computation, some gate, some logic, will give you the overflow detection logic. There's a shortcut that you can use by only checking the carry in and carry out from the most significant bit. And that allows you to use a 2-input function to implement the overflow detection. Right? So when you have 0, 0, 1 on the most significant bit, right, this is a bit of hint essentially for today's workbook. Right? 0 plus 0 gives you a 1. Right? And this is an overflow condition. And if you look at the carry in and carry out at the most significant bit, in this case, the carry in is definitely a 1. Right? 1 is the only way to give you a 1 over here. And carry out would be 0. So they differ. And as it turns out, this is also the general condition for overflow detection in 2's complement. Whenever they differ, you have 1 as a carry in, 0 as a carry out, you have an overflow. You have 0 as a carry in, 1 as a carry out, you have an overflow. And that can be implemented as an XOR function between, this is the carry out of the most significant bit, and this line is the carry in of the most significant bit, or the carry out from the previous bit. So maybe let me try that early example of 2's complement addition. 1, 1, 0, 0, plus 1, 1, 1, 1. Right. A is 1, 1, 0, 0, negative 4. B is 1, 1, 1, 1, negative 1. In this case, you do not have an overflow, even though the final carry out is actually a 1. Right. And you can play with the circuit later and then try different input combinations and see, for example, what is the representation, the range I can use this for addition and for subtraction. And just try to plug in different numbers and see at, in live how this binary addition circuit works, right? How combinational circuit works in general when your inputs go through these different gates and eventually flow to the outputs. Right. So that is my adder subtractor circuit. And this is a full gate level implementation. This is a full implementation of a 4-bit adder. We have an XOR as the carry logic, the sum logic, and the 2-level sum of products as my carry logic, and they form a chain. And this circuit is kind of slow, because whenever you send in inputs, your inputs needs to go through the longest path to complete the operation. And the longest path involves coming in from the initial carry in, or even from here, go through 2 levels, another 2 levels, 2 levels, 2 levels, until you reach the carry out. And those are 8 levels of gates. And every gate incurs a bit of delay in your computation. And you have to take their summation to get your overall latency. And this is a very big latency. And adder is such a common logic that many computation uses millions of times per second. So people do have a strong need to optimize it. So the issue with this 4-bit repo carry adder is that carry out depends on the initial carry in. And it has to flow through these 4 stages, each stage containing 2 levels of logic to produce the final carry out. The question is, how can I compute it quicker? Right? Is there any conditions that I know carry should be 1 right away? Yeah. Any ideas how we can compute it quicker? I'll give you a hint. So let's say if my input is 1, 1. I can decide my carry out right away without having to wait for the previous carry-ins. Right? 1, 1 will always produce a carry out, right? Regardless of the value at the carry-in. Or if this condition is 1, 0, and this is 1, 1, again, C3 will be a 1, carry out will be a 1, regardless of the previous carries, C2, C1, C0. This tells us that we can analyze the condition of some of these bits, 1, 1, 1, 0. They seem to have some special properties that allow you to accelerate the evaluation of the carryouts without having to wait for all of the previous carries. And eventually, the goal is to compute all of these carries in parallel. Right? Not let C4 depend on C3, but compute C4 based on some of the other input conditions in much fewer number of layers. So here are 2 important conditions that we care about. For a 1-bit adder, right, 1-bit full adder, if your 2 data inputs are 1, 1, it will generate a carry right away, regardless of the carry in. If your input is 1, 0, 0, 1, it will propagate the carry in directly to the carry out. If it's 0, 0, it's going to cut the carry out. Right? 0, 0 carry out is always 0. So 1, 1 is a condition to generate a carry. 0, 1 is a condition to propagate a carry. And these are some of the conditions that we can compute in parallel for each individual bit. I can compute the generate and propagate condition for bit position 3, independent of the other bit positions. In fact, I can compute them for each individual bit all in parallel. Right? Because this computation depends on only the 2 data inputs into each full adder. It does not depend on the carry-in. And that is the idea of a carry look-ahead adder. A carry look-ahead adder computes the generate and propagate condition for each individual bit, and then send it to like a master look-ahead circuitry. And this circuit will compute each carry in a 2-level form. This is a very complicated expression, so don't worry about this. But the idea is, if you want to compute carry-in of C1, let's say, C1 would be 1 when A1, B1 are 1, 1. And that is a generate condition. Or when A1, A0, and B0, they sit at the propagate condition, and C0 is a 1. So we can convert that into a 2-level circuit. Similarly, we can convert C4 into also a 2-level circuit rather than 8 levels. So C4 would be 1 when this one produces a generate, so 1, 1, directly sets the carry to be a 1. Or when this adder sits at the propagate condition, and this one generate, or this is propagate, this is propagate, and this is generate, or all of those 3 are propagate, and this is generate. And that can be described in a 2-level circuit. Now, if you look at the overall latency of the circuit, generate and propagate, each of them is an individual gate. So that's 1 level of logic. And within this carry look-ahead circuit, it is a 2-level circuit. It's a pretty complicated 2-level circuit, but it's 2-level. So between these GP conditions into the final carryout, you only need 2 levels of gates. Right? So overall, within 3 levels of gates, you can compute the final carryout, C4. Right? So again, in this class, we talk about design and optimization. This is the optimization part. And don't worry too much about this particular adder design. Again, this is a purple slide. So I just expect you to know essentially the principle driving this optimization is to realize that we can do some pre-computation in parallel and then make use of these bits to design a 2-level circuit to accelerate everything. Yeah. Any questions about adders? So that's everything about adders. Right? We talked about full adder, multi-bit adder, how to use adder as a subtractor, and finally how to optimize the performance of an adder. So if not, we're going to move on to the next topic, Karnaugh maps. Karnaugh map is a way for you to find a minimal two-level circuit. So this logic minimization process can be formalized as follows. We start with some specification of min terms, max terms, and don't cares. Essentially start with a truth table. And then we want to end with a two-level minimum sum of products or product sum circuits, right? With an AND gate, OR gate, or OR gate, AND gate to implement that function using number one, the fuse gates. That is the main optimization objectives. Every gate takes some transistors, and we want to minimize the number of transistors. And secondarily, the fuse number of gate inputs. Again, this reduces the length of the wires. This also reduces the number of transistors. So with more gate inputs, like 3 input, AND gate has more transistors than a 2-input AND gate. Right? They differ by 2 transistors. So we want to find the smallest circuit with fused gates, and then secondarily, fused input literals. All right. So again, let's start from some of the basics. Try it out for a NAND circuit. So NAND circuit, that is the truth table for NAND. 0, 0, 0, 1, 1, 0, produce an output of 1. If we want to represent it as a two-level circuit, right, using OR gate preceded by some AND gates, what you can do is you can represent it as a sum of min terms. Right? That is a canonical representation, the unique and complete method to represent any Boolean function. And then apply some Boolean algebra. And what I can do is I can essentially group together these two terms into x prime, right, by applying the uniting theorem. I can also group together these two into y prime by uniting them. Right, or we can think of it as distributivity followed by complement. And finally, I get a minimum sum of products. And at this point, the product is in fact so big that it's only a single level of gates. Right? Inverter, we don't typically count it when counting the circuit levels. Right? Just a single OR gate with 2 inverted inputs. And this is a lot better than the original sum of min term representation. Okay, you can solve the minimization problem from the Boolean algebra perspective. There's a second method, which is to visually check the relationship of those min terms in this two-dimensional truth table. And again, I'm representing each min term as their product term, x prime, y prime, x prime, y, x, y prime. And as it turns out, these terms that can be combined sit at adjacent cells. So x prime, y prime, and y prime, and x prime, y can be combined into x prime. These two can be combined into y prime. Right, these adjacent min terms can be combined into a combined product term that has fewer literals. Right? Or you can say you can call it a larger product term because it covers more conditions that produce a 1. Each min term covers only 1 condition, and this combined term covers 2 conditions. And that leads to a simpler logic implementation. This thing is what I call the two-dimensional truth table, but this is really called a Karnaugh map. Karnaugh map provides a very nice visualization of hemi-adjacency. X prime, y prime, x prime, y, they are adjacent in this 2D representation, and these adjacent ones can be combined into a single product. And in fact, if you look at the binary representation of each cell, so 0, 0, 0, 1, 1, 0, 1, 1, all of the neighbors sit next to each other. So 0, 0 has 2 neighbors, 1, 0, 0, 1, so they sit next to each other. And therefore, by visually grouping together a bunch of 1s, you can get a more minimal implementation. 0, 1 has 2 neighbors, 0, 0, 1, 1, and they all sit next to each other. Again, by visually grouping together adjacent 1s, you can build a more minimal function. And this is a natural way to represent Boolean algebra since 1881. So 1858, that is when Boolean algebra was born. So like another 20, 30 years after that, people start to realize that you can visually analyze this adjacency relationship by creating this 2x2 table and then fill out the 1s and 0s according to that order. Right? So that is a 2-variable function. NAND gate is a 2-variable function. And in real life, you're always building a larger function, 3 input, 4 input, and even more input variables, right? So how do I visualize adjacency for those larger functions? Let's say with 3 variables. You can visualize it in a cube. Every cell has 3 neighbors. So let's say the cell over here has 3 neighbors, 1 to its left, 1 to the bottom, and 1 to the back. Right? Again, it sits together with 3 of its neighbors. And this cube is kind of hard to draw out, and it's hard to visually see some of the relationship. So people propose a 3-variable width chart. Of course, this is by a guy whose name is Rich. So width chart is essentially separating the front plane and the back plane of a 3-dimensional 2x2x2 cube into 2 separate 2x2 tables. And in this situation, again, we can find the neighbor of every cell by going to the left, going to the bottom within the same 2x2 table, and also going to the back to the other table at the same cell position. And that's how we find out these 3 neighbors. What about 4-variable? You can do that, but it's getting a lot more complicated. You have to create 4 2x2 tables and then put them sort of like in a grid. So you have like a local adjacency and also the global adjacency. So again, if we take a look at any cell, if we look at this, it should have 4 neighbors because it's a 4-variable function. So the neighbor goes at the top and to the left in the same Karnaugh map, and also bottom and right to a different 2x2 table. Right? You can verify that 0011 is adjacent to 1011, 0111, 0001, and 0010. Right? They all differ by only 1 position, so they are neighbors. And this works, but it's just very inelegant. And here comes Maurice Karnaugh. He invented a different visualization method for 3-variable, 4-variable, and even 5 and 6-variable functions. So his idea works as follows. So you look at the 2 planes, the front plane and the back plane of that 3-dimensional cube. Right? Instead of putting them side by side, you flip the order of 2 columns. You bring the last column a little bit to the middle, and then put them next to each other. And then this gives you a very interesting advantage, which is if you look at 010, you should have 3 neighbors, 3-variable function, 3-bit binary number. So there are 3 neighbors differing with it by 1. One of the neighbors is to its left, the other is to the bottom, the other is to its right. It has all 3 neighbors sitting next to it in this particular ordering. Right? Isn't this nice? You can essentially, if you want to group together neighbors, you can just go here or here or here to find all the neighbors of 010. Such a nice visualization. Let's examine another cell. Right? So if we look at 111, for example, again, 3 neighbors, 110, 011, 101, all sitting next to each other, which is very nice. But problems arise when you look at some of these corner or edge cells. 100, again, it should have 3 neighbors. 1 to the left, 1 to the bottom, and the other neighbor is all the way over here, which is not so nice. Right? 100 and 000, they're adjacent, and they should be neighbors, but they're not neighbors. When you shuffle those orders, actually they're separated even further. They sit at the 2 edges of this table. So what you have to do is you have to visually, or in your mind, think of it as a wraparound table. The 2 ends connect to each other so that all of the neighbors still sit next to each other. And I have this Karnaugh map over here. Right? This is based on that ordering. 000 over here, 100 over here. Right? You have to think of them as neighbors by sort of like wrap around this table into a cylinder. And now 000 has 3 neighbors down next to it, and on the other side, we have this conceptual wraparound neighbor. Right? So I'm going to leave it over here. Again, 000, 001, 010, and then with wraparound, the other neighbor, 100, is also sitting next to 0, 0, 0. Right, 3 neighbors with the wraparound adjacency. And Karnaugh actually worked at the same place as Hamming. They both worked at Bell Labs for many years. And there's some relationship in their research. Hamming developed Hamming code and Hamming distance, right, a way to reason about the difference between 2 binary numbers. And Karnaugh's work is essentially an application of Hamming adjacency when it comes to visualizing the adjacency relationship of minterms. So he developed Karnaugh maps like a few years after Hamming developed Hamming distance, and they're all based on the same concept. When 2 binary numbers differ by 1 with a Hamming distance of 1, we want to put them next to each other in a visualization, and that visualization is Karnaugh maps. All right. Now we have 2 people forming a very strong team at Bell Labs. Eventually, we're going to see, I would say, 7, 8 people. They all work at Bell Labs, and this is really the place where many innovations about semiconductor design was born. So at the 1970s, 1960s, this is the place if you want to do research in digital design. Right? And do you know which company owns Bell Labs nowadays? AT&T, yes. Now, it really freaked me out. AT&T, now it's called AT&T Bell Labs. Right? They're still doing some research and some good research, but it's not the exclusive place to do research in semiconductor. Again, here I'm just showing the binary representation of these cells. 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, with a wraparound. All of the 3 neighbors sort of sit next to each other. You can create this Karnaugh map for, that is the traditional 2D truth table or 2-variable Karnaugh map. This is a 3-variable Karnaugh map. This Karnaugh map can be represented in some other alternative forms, but they're really based on the same concept. You can put 1 variable on top, 2 variables on the side to create this 2x4 or 4x2 Karnaugh maps. You can have a 4x4 Karnaugh maps. And all of these, these rows and columns, when you have 4 elements, they'll follow the 0, 0, 0, 1, 1, 1, 1, 0 orders. And this is actually called gray code. When we saw BCD, 8421 BCD, XS3 BCD, there's a table having multiple codes, and one of them is a gray code. And that satisfies this kind of adjacency relationship. Neighbor, 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 wraparound neighbor. Right? By following this gray code or Hamming adjacency ordering, you get to put all the neighbors next to each other. An alternative view of the same problem is to look at the decimal representations for these cells. And they will translate into the indexes of minterms and maxterms. So if I follow the ABC order, 0, 0, 0 is index 0, right? 1, 1, 0 is index 6, 1, 1, 1 is index 7, right? 0, 0, 1 is index 1. Again, in this table, I follow the ABC order. A on the top, BC on the side. So 1, 1, 1, that is 7. 1, 0, 1 is 5. 0, 1, 0, that's number 2. So if you have a minterm number 2, right, M2, lowercase m2, you'll probably put a 1 over here to show that in a Karnaugh map. And with a 4-variable Karnaugh map, A, B, C, D order, so 1, 0, 1, 1, 8 plus 2 plus 1, that's 11. Right, 1, 1, 1, 0, 8 plus 4 plus 2, that's 14. 0, 1, 1, 1, number 7. Again, you always have to pay attention to the variables, the axis, right? Where do I put AB, where do I put CD, and that will determine the ordering or the decimal indices of each position in the Karnaugh map. All right. So how do I put a function in a Karnaugh map? I'm going to do some plotting. By converting a minterm representation, this is a minterm expansion, and that's a maximum expansion for the same function. I just have to look for the cells corresponding to each index, and then fill it out with zeros and ones. All right. So this function has minterms 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. And to put down ones. 1, 1, 1, 1, 1. And 0, 1, 2, those are my max terms. So I just fill it out with all zeros. And now you just converted a Boolean function between truth table and minterm maximum expansion, and also Karnaugh map. These are 3 equivalent representations. Okay. Any questions so far? Yes? That's a good question. If you have 3 variables in one dimension, right? So Eric is trying to build a very large Karnaugh map. So let's say if you do a 2x8 Karnaugh map, right? 3 variables, 8 different binary combinations. You're going to run into some problems. So if I really do that, so this is how would that Karnaugh map should look like, right? And again, you can follow this gray code ordering to give them some adjacent binary designations: 000, 001, 011, 010, 110, 111, 101, 100, and wrap around, they're also neighbors. And this is one gray code ordering. You have multiple equivalent gray code orderings. You can shuffle it a little bit, shift it a little bit, rotate it a little bit. But this is essentially what you will get. Right? And now we run into some problems. Every cell, right? Look at this cell, for example. You should have 4 neighbors because this is a 4-variable function. Right? 1 variable over here. Let's call that A, and then B, C, D, and let's say over here. One of the neighbors over here, one of the neighbors over here, one of the neighbors over here, which are very nice. But where's the other neighbor? So this is your, let me use a different color. 0, 1, 1, 0. Well, this one is so faint. 0, 1, 1, 0. And then you have 0, 1, 1, 1. This is 1, 1, 1, 0. This is 0, 0, 1, 0. But this one should have 4 neighbors. Where's the other neighbor of it? Right? Where's the other neighbor? Did anyone see the other neighbor of 0, 1, 1, 0? Should be 0, 1, 0, 0. 0, 1, 0, 0. The other neighbor sits over here. 0, 1, 0, 0 is a neighbor of 0, 1, 1, 0. And they do not sit next to each other. And that is a problem. If you go to more than 4 elements in your row or column space, then you don't get to have all the neighbors sitting next to each other. You almost have to fold this by half in this way, fold it by half in the other way, to have multiple foldings to visually appreciate this neighboring relationship. And that's the reason why when we talk about Karnaugh maps, we usually just stop at the 4x4 Karnaugh map, where every cell has 4 neighbors, and they can go top, bottom, left, and right to visually see those 4 neighbors. Right? At the edge, top, down, left, and wrap around right. Right at the corner, top, left, wrap around top and bottom, wrap around side and side, right, to see all the neighbors. In this planar space, you can have 4 directions pretty easily. 5 directions is a bit of a stretch. You can do it by essentially cutting everything in half and going diagonally a little bit. 6, going diagonally a different way. But anything more than that doesn't quite work. Right? And when we want to put these things like 3 variables on one side, you just lose some of this visual capability to identify neighbors. So coming back to this example, the way we convert truth table or min-term maximum expansion into a Karnaugh map is just by finding the indices of min-terms and max-terms. Essentially, that is no different from a truth table, other than using a different kind of ordering. Right? The information contents, the output column, and the values in the Karnaugh map really they mean the same thing. Right? A better visualization, you can look at it in terms of their decimal indices or also binary indices. So for example, 3 would be 011. 011 corresponds here. 111, 111, based on the headers, goes over there. Right? Decimal, binary is really up to you. All right. This is one of the examples that we saw yesterday, the 011 comparator, that produces an output of 1 when your input is greater than or equal to 011. And that's the truth table. Again, we can map it into a Karnaugh map by following the min-terms and max-terms. And to simplify that function, again, we have 2 choices. Number 1, Boolean algebra, like we saw last time. Number 2 is directly through Karnaugh map, which is, I would say, 10 times easier. The way it works in Karnaugh map is, again, by grouping together neighboring ones. You have this whole column of ones, right? This whole column of ones. And that can be viewed as a single group. which can then be represented as a single term. That group essentially corresponds to the condition of A equals 1. Right? A equals 1 corresponds to that side, that half of the Karnaugh map. So these 4 ones can be together, represented using a single term of just variable A. And these 2 neighboring ones, again, they can be combined together. And this condition depends on BC of being 1, 1, but it does not depend on A. The output is 1 independent of the A values at these 2 cells. Right? As long as BC is 1, 1, output is a 1. So these 2 can be grouped together, and they're represented as a term of BC. So with that, you can directly go from here to the final minimal expression without ever having to worry about Boolean algebra. Yeah. Isn't this a lot nicer? Right. And I just want to remind you, in general, these are some of the ways that you can group together minterms. These, 4 ones sitting in a cube that can be combined. 2 ones sitting next to each other can be combined. Or you have to also think about this end around, the edge and corner and top and bottom adjacency. So that top one and bottom one, they're adjacent. So with this wraparound, they're also neighbors, and they can also be grouped into a single term. And how do I represent that term? Well, I essentially look for my input conditions that can represent that cube or rectangular shape of ones. The first example, they correspond to this section of the Karnaugh map, which essentially corresponds to B equals 1. And B equals 1 covers those 4 cases, right? Because you see 1, 1, 1, 0. So really, whenever the input is 1x, whenever B is 1, output is 1. So you can just represent that using a single term of B. The second one, again, we look for these headers. It says B equals 1, C equals 0. So we write it as BC prime. And finally, the wraparound one is a little bit harder to identify. Right? Just always pay attention to it. Maybe put down this one sentence on your cheat sheet saying that pay attention to wraparound implicants or product terms. So for that top and bottom, they share the same condition of A equals 1. Right? They happen on that side of the Karnaugh map. And then what does these 2 rows have in common? Well, they have different B values, but both of them have C equals 0. And that can be represented as C prime. So together, that is represented as AC prime. The rule of thumb is that any rectangular shape of the size of 2 to the n times 2 to the m, right? We have 2 by 2, 2 by 1, 1 by 4, 2 by 4, those kind of shapes, you can represent it as a single product term. All right. So here I have an exercise for you. Right? Just try it out. Try to put down this Boolean expression into the Karnaugh map by finding out, okay, what are the positions, what are the shapes that correspond to A prime, what are the shapes that correspond to B prime C, etc., and then make this conversion. Yeah, I'll give you 1 minute to work on this exercise. Yeah. If anyone has some questions when we're doing these activities, just call me out, and then I'll get to you and help you. Yeah. How to do it? So each of the term corresponds to a shape in the Karnaugh map. Yeah. Right? It's going to be a rectangular shape. Yeah. So if you have ones on the that entire right column, have 4 ones, then that is represented by an A, a single literal A. And if you have an A prime, that corresponds to 4 ones when A equals 0. Right? When A equals 0, that entire column is the condition of A equals 0. And you want the output to be 1 whenever A is 0. Right? This function will be 1 whenever A is 0, just by having the last term of A prime. A prime is the condition when A equals 0. Yes, all four of those. ABC prime then corresponds to one min term because it's specified with all the input variables. A equals 1, B equals 1, C equals 0. Going down further by 2 positions, right? 1 and 1, 0. You see we have headers of the table shown on the left and at the top. All right. Let's do this together. So I'm going to start with some of the larger implicants, the larger product terms. Right? A prime, that corresponds to condition of A equals 0. And whenever A equals 0, output will be 1 for this Boolean function. 0 complemented becomes a 1, 1 or anything gives you a 1. And secondly, B prime C, that is when B equals 0, C equals 1. And that corresponds, that corresponds to the second row, right? B equals 0, C equals 1. And then thirdly, A, B, C prime, which is when A equals 1, B equals 1, C equals 0. So 1, 1, 0, 1, 1, 0 takes me to the bottom of the Karnaugh map. Do you think this expression is minimal? It's not minimal? It's not. Why? Yes. Yes, this bottom right term, A, B, C prime, this is not the best way to group together adjacent ones. You can do a regrouping by including its neighboring cell into a larger term. And this term will be represented by BC prime. Right, therefore, we can really replace AB prime C prime, ABC prime with BC prime. And that is also something that you should be able to realize from Boolean algebra. Right, between A and this ABC prime, A is a term that can be eliminated by applying term elimination. Right, essentially, that's the very same optimization that you can get from the Karnaugh map directly. Yeah, we're trying 2 things. Number 1 is to represent functions in a Karnaugh map. Number 2 is to optimize it by grouping together adjacent ones as much as possible. Yes, Rona?
Implicitly, we have
That's right. You're essentially making this proof through a different path of Boolean algebra. So if I were to write it out in the algebraic way, you're essentially saying that, well, this expression is the same as adding A prime BC prime. That term would typically be absorbed by A prime, but I can also add it, right, by applying absorption in the reverse direction. And the A prime BC prime and this one, they can be combined into BC prime. Right, a different visualization of a different theorem in Boolean algebra in the Karnaugh map. All right, yeah, any other questions? So with that, I'm going to quickly run through many of the theorems that we have seen before from Karnaugh maps. Uniting, right? 2 different terms sharing the same variable, but having the other variable appearing in non-complemented and complemented form. So AB prime is over here. AB is over here. And as you can see, they can be combined into that single column of A. Right. Absorption. A is this whole column, 1, 1, 1, 1. AB is a smaller part of the column. That is AB. And this AB is redundant. It's already fully covered by A. And therefore, I tend to call A the larger product term because it covers more ones. The larger product term has fewer literals, which translates into a more optimal gate. Right. So keep going. Some of these more complicated theorems can also be visualized through Karnaugh map. So the first one is consensus. I have AB. So AB goes over here. A prime C goes over here. Right, this is AB. That is A prime C. And they can create this additional consensus term of BC. So BC is this thing that overlaps with both of the other 2 terms. but it doesn't provide any additional coverage, so it can also be eliminated by consensus. And then in elimination, I have A over here, A prime B gets over here, A prime B. And this A prime B is not the best way to group together adjacent ones. You can increase it to a bigger block of just B, and that is term elimination. Right? This is just to verify that Boolean algebra still works. K-map is an equivalent, or it's like a visualization of Boolean algebra, but fundamentally it follows the very same rules. All right. And this is a more complicated consensus example from Monday. Right? We have two quite different looking expressions. Again, I'm going to put both of them in the Karnaugh map. So A prime, B prime, when A equals 0, B equals 0, that's A prime, B prime. And then AC, AC is A is 1, C is 1. So this is AC. And this bottom one, that is B, C prime. B equals 1, C equals 0. On the other side, right, that is the left-hand side. The right-hand side goes as follows. So B prime C, B equals 0, C equals 1, that's B prime C. A prime C prime, that is a wraparound implicant. A equals 0, C equals 0, which are the top and bottom row. And that is A prime C prime. And then finally, AB. Right. And now if you ignore the colors, they really cover the same ones, the very same mean terms, in different ways, right? By like you're almost rotating it a little bit by one position, you get entirely different representations. But fundamentally, they cover the same ones, and both of them are equally minimal. These three product term is the minimal way to cover all of your terms, all of the mean terms. All right, any questions so far? The next thing is that we just plotted a lot of product terms. As mean terms, as larger products, you can also plot some sum terms in a Karnaugh map. Right? Some of this summation, the OR function, can also be put and visually identified through Karnaugh maps. And here, again, I'm dealing with the same function, 0, 1, 1 comparator. I have 3 max terms. And if I write them out as a Boolean algebra, Boolean expression, and then apply Boolean algebra, this is the minimal expression I got. And that represents ways of grouping together adjacent zeros, and then eventually arriving at a product of sum expression. Right? Mean term corresponds to product terms, and eventually you'll get a sum of products. And max terms correspond to some sum terms, a summation of literals. And eventually, when you put them together, you will get a product of sum expression. And over here, grouping happens in almost like the opposite fashion. I mean, in terms of interpreting the value of your input variables. So A plus B corresponds to the top left corner when A equals 0 and B equals 0. That is the opposite rule as grouping together implicants or product terms. Right here, you essentially complement each of the literal to identify the position where that product term, that sum term sits. A equals 0, B equals 0 corresponds to A plus B. And the wraparound one indicates A equals 0, C equals 0. And because it's a sum term, that is represented by A plus C. The reason? Well, now we're dealing with zeros. So we should really have the complement of the mean terms and products. And therefore, when we look at the headers of the table, 0 becomes a non-complementary variable. 1 becomes a complementary variable when grouping together zeros and then finding the sum terms. So that's everything for today. Today we talked about binary adder and subtractors. We went through the construction and some basic application of Karnaugh maps in logic minimization. We did a lot of plotting, some optimization, and then going back and forth between truth table, expression, and Karnaugh map. And tomorrow we're going to see more about Karnaugh maps to develop a systematic minimization algorithm.
For number 3, like, is this right?
Right, which means the transformation does not do anything.
Yeah,
But the transformation should do something.